number 29 of 11.3 in the second edition.
Oh, so 29 on the second edition, I also heard 40. So number 29, what did that say?
It basically said that u is equal to the square root of x1 squared plus x2 squared plus and then dot 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 dot, and then xn squared.
Okay.
And then I think we had to find the partial derivatives. So I was
Which partial
confused.
derivatives?
Just of the, I'm not sure, that's what I got confused on, it just said find all partial derivatives or something like that.
So you can only find one, there's only one.
Yeah, I thought there was only x.
Oh, no, each of these is a different variable.
But it's going to be the same for each, so.
It's going to look the same for each, so you can write out a general formula. If you do only one, so if you say that the partial derivative of this with respect to x1, what would that look like?
2x to the n.
X1 over that. 2x.
It would be
That's
x1
x1 over that, yeah.
over the radical of and they basically all look like that, except this guy would be replaced. So in general,
It'd be x2, x
you can say the partial of u with respect to xi, where I is any one of these from 1 to n, right, where I goes from 1 to n, will be xi over the radical. Or you can write as xi over u. Yeah, so that's how you do it in general, because they'll all look the same way. Also 40, this was from the second edition as well? 41?
From the first one.
That wasn't on 11.3.
Is this 11.3?
No. Oh, wait.
Number 19.
41 was in 11.3?
Yeah.
Okay, what is that question?
You find the partial derivatives of, it just said f of x and g of y.
Okay, all right, so if there was one, it's like an ABC thing,
Yeah,
where they said like z was f of x plus g of y,
yeah.
and then there was like, was it f of x divided by g of y?
f of x minus plus y. F of x plus y.
F of the open bracket.
No, all in the bracket.
Oh, okay.
X plus Y plus Y.
And c was,
That wasn't the same.
there wasn't just those two?
Yeah.
Oh, okay. So it means they want you to find the partial of z with respect to x, and find the partial of z with respect to y, I assume. Okay, what's that here? It's just like f prime. It's just plus that's 0, so it's just f prime. Similarly here, this would just be. That's it. What about this one?
F prime of open bracket x plus y times 1. This is the chain rule, right?
Right, but you can't write prime.
Oh, I'm sorry.
It's partial of f with respect to x
That's right.
of x plus y times the derivative of the inside. Okay, and so then you would have the derivative, the inside with respect to x is just 1. So just times 1.
We can use the prime.
No, because there are y's in there.
Because the prime assumes you're just differentiating with respect to 1.
To a single variable. Right. Here you could write a prime if you wanted. But here it's a function of both x and
Oh, I
y.
see what you're saying.
So
Okay.
you can't really do a prime derivative.
Number 49.
Same section? What does that say?
It's the second edition.
Okay.
It says V equals to tan inverse x plus y
In the angle?
over, no, the angle, inside the angle,
Oh, x plus y.
over 1 minus xy.
All of that like this?
Yes,
Let's find all the seconds.
we have to find all the partial,
All second partials or first
all
partials?
first partial.
Oh wait.
And second.
And second.
All second partial.
Oh,
It says find all second partials. Okay. So it means we want zxx, zyy, and zxy. Zyx. Yeah. So let's work on this guy. So first let's find z with respect to x. How do you do that? What's the derivative of tangent inverse?
1 over 1
1 over
plus
1 plus x.
1 over 1 plus the variable part squared times the derivative of the variable part, right? Which is what in this case? What's the derivative of this with respect to x, right? So you're thinking of the y as a constant now. How do you differentiate that? Quotient rule. So what does the quotient rule say?
1 minus x, y.
Right, it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And you could simplify that a little bit. So this would become 1 minus xy plus xy plus y squared over this would become 1 minus x y squared plus x plus y squared. Did anyone try simplifying it even more?
I think it's better because we have to take another.
I don't even know if it will be beneficial, that's what I was wondering. Okay, let's see. This would be 1 minus 2xy plus x squared y squared plus x squared plus 2xy plus y squared. So this would be that. Okay, and then you do zxx. How do you do that one? There's a constant on the top, so I probably wouldn't do a quotient rule again. You can think of this as 1 plus y squared times 1 plus x squared y squared plus x squared plus y squared all to the minus 1, and then do the chain rule. So it's just minus 1 plus y squared times all of that guy. Minus 2, multiply the derivative of the inside, which with respect to x, what's that? 2xy squared plus 2x. So you can write that as and that would be zxx. If you do zxy,
That's not the answer.
You've got to square the denominator.
Let's think of like dx.
all of this,
Yeah.
yeah. If you do zxy, then you have to differentiate this with respect to y, and then you're going to use a quotient rule again. This is really annoying.
Simplify dx.
Hmm?
You can simplify.
This can be simplified?
Yeah.
I feel like it could be. So,
But yeah, you could.
Cos divided by
yeah,
1 plus 5
we actually
squared.
could.
Yeah.
You can factorize the denominator.
We can do
Take x squared.
integration factor by grouping, right? So if we take out an egg, we can leave this as y squared plus 1 plus, then we have x squared times y squared plus 1, which would make it a lot nicer. So that would be actually y squared plus 1 times x squared plus 1, which is just 1 over x squared plus 1. And then this would be a whole lot nicer. I'm sure if you could factor this, but you wouldn't want to do that. This would be a lot nicer now. So you could get zxx to be, now you just want to find the derivative of that. So that's just going to be minus times 2x. So what would zxy be here? And then yeah, you do a similar thing for the walls. So you have to go through the y's.
Sure, why
No,
not?
it's the same answer. Just like in y.
So for if you did the zyy, you would have gotten 1 over y squared plus 1, you're saying?
No, the zyy is going to be negative 2y over y squared plus 1.
Okay. That was it. Yeah, so you had to do some factoring, makes your life easier. Other questions?
Can you do 119?
What does it say?
xy, like the function, is equal to the integration of,
xy?
no, the function f, then,
F of xy.
yeah, f of xy.
Okay, f of xy is equal to,
It's going from y to x. Cosine e to the part t,
e to the
t,
t.
dt.
Just that?
Yeah.
Okay, and you are supposed to find what?
The partial.
Just the first ones, fx and fy?
Yes.
Okay, how do we do that one?
Fundamental theorem of calculus.
Right, fundamental theorem of calculus. Call by the fundamental theorem of calculus. If we have f of x is defined by an integral from a constant up to a function, f of t dt, then the derivative is just f evaluated at the function times the derivative of the function. This fundamental theorem, second fundamental theorem of calculus with chain rule built in. So basically, this is the theorem. You have to have a constant on the bottom and a function on top, which means this you'd want to rewrite as something like, I guess, 0 to x minus 0 to y.
And that's because we're inverting the limits of integration.
Yes, I think of this as y up to 0, blah, 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 plus 0 to x, blah, blah, blah. And then to flip the limits, you just take the negative of the integral so that it looks like this. Once it looks like that, I can start to differentiate now. So the partial with respect to x would be, this is going to be, if we start differentiating, this is actually going to be a function of y, so you can sort of ignore. So here, this would actually be given by cosine e to the x times x.
I did it totally differently, and I got the right answer according to the back of the book.
What did you do?
I wish I knew. I just took the integral of cosine e to the t.
You can integrate that.
Because you have ET.
We can integrate integral of cosine e to the t. There's no
You can't do it
answering
with u
element.
substitution?
Nope.
Okay, but I got the right answer.
You cannot write the answer for that in transcendental functions. It has no elementary integrals. Just like integrating e to the x squared. Can't do it.
Okay.
Other questions? $11.4 maybe?
Number 5. 11.3.
What did that say?
If f x y equals 16 minus 4x squared minus y squared, and find fx 1, 2,
Like that?
and fy 1, 2. I
Whoa.
don't know how to draw the graph.
Oh, did they say draw a graph as well?
Yes.
Yes.
Like the slope.
Okay, we
And
could.
fy 1, 2.
Let's find these guys first. Fx would be what? Minus 8x, so fx at 1 comma 2 is just minus 8. Fy is minus 2y, so fy at 1, 2, just minus 4. For the graph, they're really asking you to draw z equals 16 minus 4x squared minus y squared. How do you do that?
Set one, either x or y,
So they said two
equal
of
to
them
the
equal to
point,
zero,
and then
one of them.
draw it on that plane.
Right, you can do traces if you don't know. They're all parabolic. So if you're looking in the xz plane, this plane over here, you'd really want to draw z equals 16 minus 4x squared. So it goes up to 16, and it goes like that. That will come down. And that's in this wall. In the other wall, you have 16 minus y squared. Like that. So it's sort of elongated. It's sort of, but it's an upside down parabola.
In the book, the illustration also shows like the curves that the derivatives are tangent to and stuff like that. So
Oh, so you try to do like 1 and 2, which drawn by your hand, that's crazy. All right, it's going to cut through here at some point. So if you want to find the partial with respect to x, it means you're going to slice it parallel to the x direction is going to look, the cut is going to look like something like that. Right? And then you're going to have like a tangent line coming here. Here you're playing with switch. This would be f1 comma 2 equals minus 8. And then for the y, you slice it this way. Yeah, that you draw with traces, right? You just realize if you look at it this way, it's just an upside down parabola. Look at that, it's an upside down parabola. So you have two upside down parabolas. Other questions?
Can we do the pronoun?
What's 59?
Okay, it says a function of, f of x, y, and z equals xy squared and zq plus r sine.
Plus?
Xy squared zq plus r sine x radical z. What's the number? 59.
You did it assign 59.
Find x to the 1.
I didn't assign 59?
No.
56 is the last one.
Yeah.
Jeez, you're doing extra overachievement.
I'm not sure to be
You should like spend hours on that problem.
Stuck around to
11.4? Yeah? Yes? Kelsey?
I had pretty much questions with a lot of the linear approximation stuff. So, yeah, I kept getting strange answers for 19.
Okay, what did 19 say?
It had f of x, y, z. And then it said that equals to the square root of x squared plus y squared plus z squared.
Okay.
And then they gave like I guess a point or something, 3, 2, 6. And then they gave like
3, 2, 6?
as like an ABC or something like that.
Okay.
I think that's how I interpreted it anyway. And then as they said, like they basically implied, I think, that the XYZ was 3.02, 1.97, and 3.99.
You want to approximate, I guess they asked you to approximate.
Should I read
this.
the question?
Yeah.
Yeah, you can do that.
It says, find a linear approximation of the function f of x, y, z equals the square root of x squared plus y squared plus z squared at 3, 2, 6, and use it to find the approximate number of the square root of 3.02 squared plus 1.97 squared plus 5.99 squared.
Okay, and that's just actually asking you to approximate f of this number. Okay, let's find the linear approximation. How do we do that?
So we find
L of xy is equal to f of the ABC plus fx evaluated at ABC, x minus a, plus fy evaluated at ABC, y minus b, plus fz evaluated at ABC, z minus c.
If you ask us to write this formula, do we need to show that it's evaluated at ABC, or is that implicit? Like, will that be implicit?
It will be okay to do that. I'll say it's okay to do that. Yeah, technically to be correct, you should write this. I think it's cumbersome and then it looks messy. Yeah, but it's implied that you're evaluating these guys at this point. Okay, so here, if we take, so that's going to be what we're going to use. Here, if we use fx, what's that?
2x over the expression.
x over
X over X squared.
Okay, x over this guy.
Yeah.
The others are very similar.
Y over.
Alright, so fy is just y over that guy. just stay over that guy. And so your f is just the radical of x squared plus y squared plus z squared. And if I evaluate f at 3, 2, 6, what did I get?
7.
It's 7?
I got radical 77. That's where my confusion began.
That would be 9 plus
3 radical
4,
49.
13, and 36. That's 49. It's 7.
Yes, somehow I ended up doing that wrong. So
Okay,
that's why
and
I
so
wanted-
your fx at the point 3, 2, 6 is going to be, the x value is 3, so it's just 3 over 7. Fy is 2 over 7. And fz at that point is 6 over 7. So the linear approx is L of x, y, z equals, this is a 3 variable one, equals 7 plus 3 over 7 times x minus 3 plus 2 over 7 times y minus 2 plus 6 over 7 times z minus 6. This implies that this guy is equal to f of this. Which is approximately, just plug in this x, y, and z into that function. Minus 2 plus 7 plus 5.9 6. This is 0, 2. That's 6 over 7 times. minus 1. Okay, so that's 7 plus 6 over 700 plus minus 6 over 700. And that's minus 6 over 700. So it's just 7 minus 6 over 700. Which, multiply that by 700, you have 4900 minus 6. 39 over 700.
So the book, it gives a different answer.
What would it give? Did it just put in
It gives
decimal?
something with the x, y, and z. They don't put the x, y, and z.
What do you mean?
Like, the book says that the answer is 7 plus 3 over 7 x plus 2 over 7 y plus 6 over 7 z.
Yeah, we have that here.
No, but they don't have the minus, like x minus 3, y minus 2, z minus c minus 6. You have
Yeah,
the
we just
book,
put
right?
it in terms of
Can you see
x,
the
y, and
answer?
z.
Here.
That ABC. What's that?
It's number 19, 11.5.
Here.
First, it
Javon?
wants you to find the linear approximation,
It's right
and
here.
then it wants you to find at the number. So you just write
Number 19, you said?
Mm-hmm.
19.
Number 19, 11.4.
Sorry.
11.4.
He has it there.
11.4.
they asked for, oh, they only want, did they ask for the function part, or I didn't have to see how the question was asked?
Well, I'll get it back for you, if you want to see it.
Find the linear approximation of the function at 3, 2, 6 and use it to approximate the number given.
Yeah.
But in the back of the book, they do give that the linear approximation just in terms of like 3/7 x plus 2/7 y plus 6/7 z. No, that's just like an abbreviated.
It's just because we didn't.
Yeah, I think they stopped before we kept
You
going.
just didn't plug in X1.
I
Yeah,
don't know.
Yeah, I don't know why they did
Probably
it.
this.
This would be it. Like when you did this, what if you plugged in this into, does anyone know how we calculate it?
That's right, yeah.
Yeah, that's right.
Yeah. So that's how you should do it. I don't know what they were doing.
So if you don't have that part, that's like minus.
Yeah, like if I asked the question, that's what I'd expect you to write down.
which one, the L?
Yes, that's called the linear approximation. Other questions? Everyone knows how to find a tangent plane?
The relationship between the tangent plane and the total differential is the same form, right, basically.
And the total differential?
Yeah.
No, the total differential gives you the change. It's not exactly the same. So a tangent plane is actually a plane, right? So if you have z equals f of x, y, this is the situation, then the tangent plane at the point, say A, B, at the point where xy equals A, B, is z minus, let me say ABC. Let me be consistent. I think I used x naught, y naught, z naught last time. So it's z minus z naught equals fx, x minus x naught plus fy, y minus y naught. Right, where fx and fy are evaluated at that point. Right, so that's the tangent plane. Now if I'm talking about the total differential, that's just dz equals the partial of f with respect to x times dx plus the partial of y with respect to y, f with respect to y times dy. Where this is sort of your change in x and your change in y. Right? It looks the same, but it's not exactly the same. This is more like, it sort of looks the same. Never noticed that before. Differential looks like a tangent plane. Which makes sense, because you use a differential to approximate how the surface is changing, which is what you use a tangent plane.
That was why I asked you last class if that is a tangent plane.
So the difference is that dz is not z minus z0?
Technically it isn't. Technically this would be more like a delta z.
So what's the difference? Isn't delta z dz?
No. No.
What's the difference between them?
Delta z, this is actually the distance between z and z naught.
Okay.
This is actually the distance between z and the approximation of z naught on the tangent line. It's like, remember the whole point of using tangent lines is to approximate curves. So let's say you have a curve that looks like this, right? And you're moving from, say, here to here. This is your x0 where you started. This would be your x. Right? Now what you can do is you can approximate this with a tangent line. You can put a tangent line here. Right? Now you see the actual distance between the points that's called delta y. The actual distance between the point and the tangent line is dy. Right? dy implies that you're using the tangent line to approximate a distance rather than the actual function. Right? But the idea is, if you zoom in close enough, this will be so close together that they're pretty much the same thing. But technically, by definition, they're not. Right? This one has more approximations going on, where this is like, that's the distance. So that's the distance between delta y. So like that, it's the actual difference versus the difference you get by approximating with the tangent line. That's the difference between the delta and the d. So with the d's, d implies that you're using a tangent line approximation to measure a distance, whereas when you use delta z, you're measuring the actual distance. That's sort of the difference. So it's not exactly a tangent line, but it looks pretty much the same.
Because in one of the questions in the book, I don't remember which one, but it said, it said d, like, it basically showed that dz is the same as delta z, and like dx is the same as delta x. I don't remember the exact
There's
case.
a map, there's an example in the book with DZ and del Z.
Yeah.
They're different.
They were different. Right. So it's like if you measure the distance with your calculator and then you just do this by hand to get it the easier way, there will be a slight difference. But depending on the function and how close you're zoomed in, it shouldn't be that much. How do I do that?
So we find the effects and FY.
Partial derivatives.
Okay, so if you call this f, we can find fx would be
Y.
y would be x, then what?
So FX is 2.
So you want to plug in f at 1, 2 is 2, fy at 1, 2 is 1. What's the third coordinate?
No, you plug in 1 and 2 in the first.
You plug in 1 and 2 here.
Yeah.
So it'll be 1 times 2 is 2, plus 3 is actually 5. Your z at this point is 5. By plugging into here. So now what's the tangent plane? Z minus
5.
the 5, right? It's the z coordinate for the point. Equals
2 into plus 1.
1 times 1 minus 2. That would be the tangent plane at the point where your x is 1 and your y is 2. Things like that you should be able to do. So this is the way you'd find a tangent plane if your z is defined explicitly. Later on we're going to learn how to do it if your z is defined implicitly. That's nice to show after we've done gradient fields, gradients and stuff. Okay, I guess that's it. Pass up the homework and put your stuff away. Oh, and I'm thinking of making the second test. Maybe.
I don't know. I was like, I don't know where we're having it.
What? What did you say? So I'll I'll definitely finish chapter 11 by next week, maybe in the middle of the week. But that Thursday is probably too soon, so maybe I'll move to the Tuesday. How about July 1st? Let me make sure.
You can't do that, it's Canada Day.
What? It's Canada Day. Okay, so again, I'll post a review problem soon and you can start practicing on that. Calc 1, hopefully. Unfortunately, the formulation that we're going to use here is the sort of the one that no one ever remembers. That's the one that we're going to use. So, yeah, you remember the chain rule says that if you take it talks about differentiating composite functions, right? So if you take the derivative of f of g of x, the chain rule says, well, you take the derivative of the outside function and then you multiply it by the derivative of the inside function. Right? So everyone remembers that rule. There's another way to say it, right? Where they use the Leibniz notation. They can say that the d dx of some let's say y is a function of x. Say y equals f of x, and your x is a function of something else, like a function of t. Right? Then you could say that dy dx is equal to dy dt is equal to dy dx times dx dt. Right? So this was also another formulation of the chain rule that you were told, but no one remembers that one, everyone remembers this one. But this is the one we're actually going to use. For multivariable functions, except the difference is here we're going to have a sum of functions. You're pretty much going to have to do this for each variable and then add them together. And that's basically what's going to happen. You can prove why this is true using differentials, but we won't prove it. I'll just tell you what the chain rule says. We will first break the chain rule into cases. So your book breaks the chain rule into cases, so we're going to go through them case by case and then do an example. Chain rule case 1. This is when you have a multivariable function and each of the variables are defined in terms of a single other variable. This is called case 1. So this is if right, so it's very similar to this case where you have something in terms of a function, but your inside function is defined in terms of another variable. Right? But here now we have two inside variables, and each of those are defined in terms of another single variable. Then you have to write out those variable functions of t dt, then if you wanted to find dz dt, you'd have to do dz dx, dx dt plus dz dy by dy dt. And this is because z will change independently. If you vary the x, it will change a little bit, plus it will change a little bit if you vary the y. And so you sort of have to add these differentials together. But it's basically the same rule, it just extended.
Shouldn't that be
dz dy times dy dt. Another way you can see it is, it turns out that the things you don't want can sort of, it looks like they can sort of cancel and leave you over with what you want. So the dx should cancel with the dx, the dy would cancel with the dy. And that's what the rule looks like. So this is case one. You have several variables, but each of them are defined in terms of one single variable. Another variable, like a parameter. Do I have an example right after? Yes, I do. Example. Let's say I told you that z is equal to the sine of xy, but also that x is a function of t, and y is a function of t. And I want you to find dz dt when t equals 0. Okay, so let's work through this one. Z is a function of x and y, sine of x times y. But your x and y themselves are defined in terms of two other variables, right? I want to find the derivative with respect to t, right, the inner variable, at the point where t equals 0. Find what?
Find the partial of x and y with respect to t first.
Sure, you can. You're going to have to do all of them. So here, if you have dz, let me just write it out first. Here, dz dt, according to our formula, is dz dx times dx dt plus dz dy. These should actually be partials. Because that is a two variable function. You can't really use a d either. Correct that here. When you're differentiating z, it has to be a partial derivative because it's a multivariable function. Okay, so we have that, and now you just plug in the pieces. What's the partial of z with respect to x?
1.
Y cosine xy times the derivative of x with respect to t.
9t squared.
Plus partial of z with respect to y
X
times the partial of y with respect to t is just 4. Now when t equals 0, you're going to need to know what x and y are in order to plug them in. So when t equals 0, your x is 7, your y is minus 2. This means dz dt when t equals 0 is equal to, you plug in minus 2 times cosine of minus 4t. Well, that's all times 0 because your t is 0. Plus x is 7 cosine 14 times 4. So that's just 28 cosine 14. Okay.
It's
Yes.
not negative.
It's negative?
Cosine is an even function.
No.
Where?
The y.
Where's the y?
Negative.
Where? Where's the negative? Y is minus 2. Is that what you want?
Anything?
Yes, cosine of minus x is equal to cosine x. Cosine is an even function. So here, same thing. I mean, there's nothing. We're really just following the formula. So let's just do this. dz dt is equal to dz dx x dt. This is equal to, what's the partial of that with respect to x?
It would be natural log of open bracket x plus 2y plus x times 1 over x.
And all of that times dx dt.
Cosine.
Plus partial with respect to y is what?
X. 2x over x plus 2y.
And all of that times
Negative.
Negative.
negative sign. So you can change this to a minus and put a sign. That's that. Now sometimes you can go in and you can swap out the x's and y's for their functions of t, but I won't require that you do that. I mean, if you ever need to figure out points, you can just do what I did here. You can actually solve for the x and y if you ever need to plug them in. So that would be a fine as the answer. Another one. dwdt equals what? Without looking in your notes.
So it's 2x.
No, the formula. Right out yours.
dy. times dy dt.
Okay, now you find the functions. What's dw dx partial with respect to x?
2xy minus 0
Times dx dt
Cosine
cosine 3
partial with respect to y
x squared minus dy
times dy dt. Notice here I'm using brackets. Very important, because if anything has to distribute, you have to know. And so when, again, t equals 0, we have x would be
0
and y would be.
1.
This means that dw dt at t equals 0 is equal to, you plug in x equals 0, that dies, you plug in x equals 0, that dies, and then you just have minus 2 times e to the 0. So minus 2 is easy. Okay, not so bad. What if your functions of two variables, right? So your z is a function of x and y, it's differentiable. And now your x is a function of s and t. Y is a function of s and t. And they're differentiable in terms of their respective dependent variables. Then you can actually find the partial with respect to each of the independent variables. So you can find dz ds and dz dt. Notice now you still have a partial here because you have two independent variables to worry about. So you can actually do it with respect to each one. Now how are you going to guess you do it with this one?
So it's basically the
dx ds, right? And notice here you have a partial here as well because your x is a multivariable function. Plus partial z with respect to y, partial y with respect to x. S here, z with respect to x, x with respect to t, plus z with respect to y, y with respect to t. So you can actually do it piece by piece. In that case, you have examples of that? Of course I do.
And these are all in partial notation.
They're all in partial, because even your inner variables are multivariable functions. So, example. Z equals 2xy. But my x is actually s squared plus t squared, and y is s divided by t. Okay, what's this? The ZDS equals, tell me the formula.
ZDS.
Okay. From now on, we're going to call these partials, not these, okay? Because these are,
Aren't they technically lowercase deltas?
yeah, but call it a partial. Call it partial.
Okay.
So partial Z, partial X, partial X, partial S, right? When you say ds, dx, you think of calc2 differentiation. It's not, technically it's not the same thing. Okay, so what do we have here? Partial Z, partial X is
2y.
partial X, partial S.
2x.
One of the T.
So that's 4sy plus 2x over t. Okay. Partial z, partial t
2y.
is partial z, partial x, partial t, plus partial z, partial y, partial t. Right? First time you learn a rule, the first few times you're doing problems, you keep writing down the rule over and over. That's how you sort of internalize it and memorize it. So, find this with respect to x, it's going to be the same guy here, to y, s with respect to t.
2x negative s over squared.
Okay, not so bad. Of course, this can be generalized. I believe in your book they wrote down the general formula, and I don't know if I want to write it down. Probably just confuse people. Say x is in terms of x1, x2, xn, where you have x1 is a function in terms of y1 into yn. Then you can say the partial z with respect to the partial of one of these y's, like y1 for example, is going to be partial z, partial x1, partial x1 with the partial of that y, plus partial z, partial x2, partial x2 with the partial of that y, partial z, partial xn, partial xn with respect to that y. There's a mnemonic to remember this. Some people like it, some people don't. I never really do it, but if you do it, I'm not going to kill you, so I might as well show you. You can use what's called a tree diagram to sort of figure out how you want to get to the partials. So, example, here if you have z is a function of x and y, where x is a function of, let's say, s and t, y is a function of y, s and t as well, then what you can do is you start with the outermost function and then you break it down to the inner function, the inner variables. So you have z, which you can break that down into functions of x and y you can break that down into functions of s and t. Right? So So if you move along an arm, it's taking a partial derivative. Find all ways to get to the independent variable you want. And some. What do I mean by that? Well, say you want partial of z with respect to s. You're going to figure out all the ways it can get to s at the bottom floor by starting at d with z at the top. How many paths do you have to get to s? There are only two paths. You'd have to go here, go to the x, then go to the s. Right? Then you can go here, go to the y, then go to the s. Every time you move along an arm, you're taking a partial derivative. Right? So to get to s, one path is to go from z to x. That means you take partial of z with respect to x. And then you multiply by partial of x with respect to s. Plus, then you take the other path, right? Partial of z with respect to y. Partial of y with respect to s would be the other arm of the path, right? Or let's say z is a function of x, y. W is a function of x, y, z, where x is x of st, y is y of st, z is z of st. In this case, your tree diagram would look like, starts at W, you can have three guys, X, Y, or Z, but each of these you have two guys, S and T, S and T, S and T. So if I wanted to find the partial with respect to T, I look at all paths where I can get to the T's. Right? Starting from W, I can go this path and get a T, or I can go this path and get a T, or I can go that path and get a T. There are three arms, which means I should have a sum of three terms, and then each arm gives me a partial. So it's W with respect to X, then X with respect to T. Plus W with respect to Y, then Y with respect to T. Plus W with respect to Z, Z with respect to T. Right, and we can keep breaking these down. Right? No matter how many variables they give you, you just have a bigger tree to find all the arms. Right? That's basically how you can remember it, if you're not into the notational way of remembering it. I want to get to implicit differentiation, because that's going to be the cool part. But first, let's do an example of one of those crazy ones. One like that. You can see here that your problems with these kinds of problems are going to be like how to differentiate, remembering all your rules from Calc 2, right? You don't really have to be visualizing things in 3D here. You just have to remember, how do you differentiate that again? Yeah, so this is very calculus 2 intensive part. You don't need to really visualize anything. Just know how to get to the formula and brute force it. So example, let W equals xy plus yz plus xz. And x is equal to s cosine t. Y is equal to s sine t. Z is just equal to t. Find partial of w with respect to s and partial of w with respect to t when s equals 1, t equals 2 pi. Find the values of the variables first. When s equals 1, t equals 2 pi, this means your x would be equal to what? X would be 1, y would be 0, z would be 2 pi. Okay, so now if I want the partial of w with respect to s, what's the formula?
Partial of w, partial x, partial x, partial
Mm-hmm. So now we have partial w with partial x is
y.
partial x with respect to s cosine t with respect to y, x plus c sine t plus y plus x times 1. So now if I want to,
There's no
I want to evaluate this at st equals 1 comma 2 pi. I'm going to evaluate this at st equals 1, 2 pi.
before z there's no s. Only 0.
Come again?
The partial for z there's no s variable in the function.
Z equals T
Where is it?
Z equals t.
Oh, yes, this is actually 0.
times
Yeah, the partial of this with respect to s is 0. So now if we evaluate that when our y is equal to 0, z is equal to 2 pi, cosine would just be 1. Right? So that's just 2 pi plus x is 1, z is 2 pi. But then cosine of 2 pi, that's going to be 0 as well. So that's just 2 pi. If I take the partial of w with respect to t, these guys won't change. This is just y plus x with respect to t is what?
Negative s times 2.
So with respect to y is just y with respect to t. W with respect to z was y plus x. Z with respect to t was 1. I want to evaluate this at st. We're evaluating this at st. Plug these in. Our y was 0, z was 2. Well, this is 0 because of the sign. Here we have x is 1, z is 2 pi, s is 1, cosine of 2 pi is 1, so it's just 1 plus 2 pi, plus y is 0 and x is 1. Okay, any questions on that? Last topic of this section, differentiation. Now remember implicit differentiation you're doing in Calc 2. We even did some on the homework so far, right? We had to sort of go through everything and differentiate, then you have to remember that if you're thinking of this as the dependent variable, you have to put the partial there, and then you have to use this algebra and solve for it, and then, yeah. Too annoying, right? There had to be a better way, and there actually is, right? So, and it's so much easier. I mean, I taught Calc 2 here before, and they're like, why didn't they teach this? Well, they didn't teach about partial derivatives. So can I use this? I don't know what your professor will say. Okay, so we can actually do implicit differentiation a lot easier than we've actually been doing it up to now, and we can do because of partial derivatives. It's going to be a nice, and in the quiz I actually asked you to write down the formula for it. So let me say f of xy equals 0 defines an implicit function we use the chain rule. So now say we let set w equals the f of xy, then if we take the partial of w with respect to x, did I actually go through that? Yeah. If you take the partial of w with respect to x, what do you get? Right, the chain rule, the same thing we've just been doing.
dw dx.
Hmm? What did I get? Partial of f with respect to x. Then you take the partial of x with respect to x. It's one of those weird things. Okay. Then you take the partial of f with respect to y. Partial of y with respect to x. But remember, in this case, since I'm thinking of these as single variables, these are actually your d's, right? Like derivatives. Because I'm not assuming that these guys are defined in terms of other functions. right? Now, since w equals f of xy, and we're assuming that f of xy is 0, this means that your w is actually 0, which means that your partial with respect to x is actually 0, right? So you can say that 0 is equal to partial of f with respect to x times 1 dx dx plus partial of y, partial of f with respect to y times dy dx, right? Then you'd actually be able to solve for dy dx. So it's going to be minus partial of f with respect to x divided by partial of f with respect to y, or in the nicer notation, dy dx is equal to minus f sub x over f sub y. Right? So now you can actually cut out all the algebra middleman. You don't have to do it. Take the partial with respect to x, put it on top, partial with respect to y, put it on bottom, put a negative sign. Done. Implicit differentiation. Let's see it in action. And then you'll never go back to the old way again. Yeah, just look at it. Just look at a random, go back to your Calc 2 notes and look at one of those problems you used to get with implicit differentiation. It took you like 15 steps. And then do it with that way. And then you're going to see. 2 steps and you're done. Okay, let's do an example. So let me write out the other general formulas. So this is one general formula. I don't know how you're going to remember this. Just remember that the variables sort of switch. Right? So y on top, x on bottom, now x on top, y on bottom. I don't know. Just, it's not that big a deal. Just remember this. Okay, so similarly, if you can write a function in 3 variables as 0, where z equals f of x, y is defined implicitly, then you can have the following. You can actually take the partial of z with respect to x. Right, so even in this homework, the last homework, you did some of these problems. You can redo them with this method and you'll see it's a lot easier. Those two would hold. So let me show you an example. Suppose if y cubed plus y squared plus 4 equals 5y plus x squared plus, why did I do, that's like really easy. Okay, no. Find dy dx. That one wasn't so bad. I could probably throw in some more x's in here or something. But even if you do this with implicit differentiation, you're going to see it's going to be sort of annoying. Yeah, so the chain rule, the dy dx is just going to be equal to negative of, you're going to take, oh, let me rewrite it first. So you can see, we can write this as y cubed plus y squared minus 5y minus x squared plus 4 equals 0, right? And then I can take this as the f. And so dy dx is just the negative of the partial with respect to x divided by the partial with respect to y. That's going to be the negative of What's the derivative of this with respect to x?
2x.
Minus 2x divided by partial respect to y.
3y squared plus
3y
y.
squared plus 2y minus 5. And that's your answer. Slightly harder one, more like your homework problems. 3x squared z minus x squared y squared plus 2z cubed plus 3yz equals 5. Find partial of z with respect to x and partial of z with respect to y. So before this, we were going to have to do this by the product rule. Remember, when you're doing the z, you have to put dz dx, right? Partial of z, partial x. And then you have to go through, you're going to do this with partial z, partial x over here. You're going to have to group those terms, bring stuff to the other side, divide by the, yeah. No. So here you can just write this as 3x squared z, or you can notice there's a constant over here, you just bring it over, it's not going to matter. X squared y squared plus 2z cubed plus 3yz minus 5 equals 0. Take this as your f of x, y, z. Then your partial of z with respect to x is just going to be negative fx over fz, which is just going to be the minus, what's partial of this with respect to x?
6x minus 2x.
That's it, right?
That's it.
Partial of this with respect to z.
6z plus 3.
No,
Oh,
this.
whoops.
3x squared, 0.
6z. 3y.
3y. That's it. Now, if you have done the whole thing like you did in the last homework, blah, 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 group terms, bring over to the other side, divide, you would have gotten that. Go back and check.
Better late than never, right?
Partial of z with respect to y. This is just going to be minus fy over x over z. So denominator is just going to look the same as that one. 3x squared plus 6z plus 3y. The top is just the partial of this with respect to y, which is going to be minus 2x squared y plus 3z. Done. One step. Right? What if I ask you here about partial of y with respect to x?
That would be fy over fx.
You put fx over fy. Right?
Oh, yes.
So fx we already found, that was up here. So this will just be minus 6xz minus 2xy squared. Divide by the fy, which I had here, minus 2x squared y plus 3z. One step. Right? That's how implicit differentiation should have been taught. But they couldn't tell you because you didn't know what a partial derivative was. And yeah, I guess on that note, we end.